All right, let's dive into one of the coolest parts of building any electronic device, firmware development. This is the magic, the invisible code that makes all our favorite gadgets actually do something. Let's get right into it.
So have you ever stopped to think about what's really happening inside your smartwatch, or your smart coffee maker, or even the complex systems in your car? What's the spark of intelligence that takes a chunk of plastic and metal and turns it into something useful? Well, it all comes down to something called firmware.
You can think of firmware as the secret ingredient. It's this special, low-level software that lives right on the device's main chip, its microcontroller. Its whole job is to be the bridge between the physical hardware, the actual sensors and circuits, and whatever higher-level software you might interact with. It's the code that makes things happen at the most fundamental level.
Now, to write this firmware, you can't just use any language. You need to speak the hardware's native tongue. And for that, developers almost always turn to two incredibly powerful, time-tested languages, embedded C and C++.
And working in these languages gives you some serious superpowers. You use things like pointers to reach directly into a specific memory address and talk to a piece of hardware, or the volatile keyword, which is a neat little trick to tell the compiler, hey, don't get clever and optimize this variable away. It could be changed by the hardware at any second. But the real nitty-gritty, the absolute core of it, is bit manipulation. We're talking about literally flipping a single bit from a 0 to a 1 to turn an LED on. It is the most direct, fundamental level of control you can possibly have.
So when you're ready to start controlling that hardware, you basically come to a fork in the road. There are really two main philosophies for how to do it, and each one has its own pretty distinct pros and cons.
And this slide just lays it out perfectly. On one side, you've got register-level programming. The best analogy for this is driving a manual car. You have total, absolute control. You get maximum performance, a real feel for the road, but it's way more complex. You'd go this route for things where every single microsecond counts. Think mission-critical stuff like a pacemaker or a car's anti-lock braking system. Performance there is non-negotiable. Then on the other side, you've got the hardware abstraction layer, or HAO. This is like driving an automatic. It's so much faster and easier to just get in and go, but you do give up some of that fine-grained control.
That car analogy is great and all, but the difference becomes so much clearer when you see it in the code itself. So let's look at how you do the exact same simple task, just toggling an LED, using both of these methods.
Check this out. Up top, you see the register-level way. We are directly accessing the output data register, or ODR, for GPIO port A, and then we're using some bitwise magic to flip the fifth bit. It's super fast, super direct, but maybe not super readable if you're new to it. Then look at the HAO library version below it, HAO GPIO toggle pin. It's doing the exact same thing under the hood, but it's wrapped in a function that you can actually read like a sentence. You're trading that raw, direct access for clarity and ease of use.
So, we have our tools, and we know the two main ways to approach the hardware. But how do you actually get from a cool idea in your head to a finished, working device? Well, the whole journey follows a pretty well-defined workflow.
Now, the source material we're looking at actually outlines a really detailed 10-step process, but you can boil it all down to these 5 core stages. First, you plan everything out. Then, you get to the fun part. You code the logic. Next, you flash it, which is just the term for loading your compiled code onto the chip itself. After that, inevitably comes debugging, where you iron out all the kinks. And finally, you maintain and optimize it for the real world. It's a clear, repeatable roadmap that works every time. Okay, so what does all this look like in the real world, on actual hardware you can buy? The really cool part is that these core ideas apply everywhere, but the level of abstraction, how much the messy details are hidden from you, can change dramatically from one platform to another. This slide is just awesome because it shows it so clearly. Look at this. To turn on a single LED, the STM32 example uses that direct register-level C code we just saw. You're right down in the guts of the hardware. Then, the ESP32, which often uses the super popular Arduino framework, abstracts that all the way into a simple command, digital write. So much easier, right? And then you have the Raspberry Pi, which is a full-blown computer. You can control its hardware pins using a high-level language like Python. It's the same exact goal, just achieved through 3 totally different layers of abstraction. So, to wrap this all up, what are the big things you need to remember? First, firmware is that vital software bridge that makes hardware actually work. Second, you've always got this choice to make between the raw power and control of registers and the speed and simplicity of a HAO. Third, the process isn't chaos, it follows that clear path: plan, code, flash, debug, and maintain. And finally, the way you write code really depends on the platform's level of abstraction.
Once you get a handle on these fundamentals, you basically have the map. You have the blueprint to take any electronic idea, no matter how wild, and turn it into a real, tangible, working device. So the only question left is, what are you going to build?